And I'm going to explain the rules of the lab so much. Tomorrow is my intention that we're going to execute the lab, which means you'll have to be able to do the lab, whether you're here or at home. The first thing you must have are coffee filters. Now, that's plausible you don't have some at home. There are lots of alternatives to coffee filters. But when I tell you about what the project is about, or the lab I mean, you'll see why maybe having some coffee filters will be helpful. So if you don't have coffee filters, you have to let me know what your substitute's going to be. I will be providing coffee filters for the classroom because they are cheap and disposable. So we're going to use the coffee filter to test terminal velocity. That's tomorrow's lab. And we talked just briefly about this at the end of class. And I want to use that brief kind of discussion to kind of go a little bit further. I said yesterday that drag, there's two types. That generally, there's the possibility of laminar drag, which has a constant that is proportional to V, and there's possibility of turbulent drag, which is proportional to V squared. We don't know which type we will have with the coffee filters. We don't know whether they go fast enough to create turbulent drag or whether they will stay in laminar drag, which is part of the problem with this lab, is we have to do two separate analyses to see whether we can use this and count on that as our form of drag or this as our form of drag. We do know that there's two conditions for the fall of our object. There's the t equals 0 condition, and then there's what I call this steady state condition, where t has been a long time. I say infinity, but infinity in this lab is about less than a second. That's about how long it takes for you to be in terminal velocity if you're a coffee filter. Now, herein lies the problem. Reaching terminal velocity depends on your value for c. It also depends on your mass, because at t equals 0, the velocity equals 0. And in that moment, the net force equals ma. And the only force acting on the system when we first release it is gravity, which means when we first release it, the object's going to accelerate at the acceleration of gravity. We're not going to take any measurements at that moment. We're going to wait. We're going to wait until it's falling at a constant velocity. Lucky for us, that happens really fast, like really fast, within moments. In the classroom, we can actually use our data capturing devices, our lab quests, to capture data. And we will send some of that on to our friends at home. But the truth is, this thing goes to terminal velocity really fast. Now, consider terminal velocity for a minute. At terminal velocity, the net force equals 0, because it's at that moment that the upward force and the downward force reach balance. I'm looking at right now the laminar as our potential for that, but you could just as easily put turbulent. Under those conditions, mg minus cv equals 0. So mg equals cv, where this is the terminal velocity. I put a little t there. What this means is our terminal velocity is proportional to how much mass there is. So in a lab, here's your goal. Your goal for this lab is twofold. First, you need to figure out which type of drag you're seeing with your data, which means you have to test whether you get a linear function with v or whether you get a linear function with v squared. We're going to try and linearize both sets of data, treating it first as if it's proportional to v, and then taking the same set of data and seeing if it's proportional to v squared. And then you will have to decide, and it's different for each lab group, whether you had laminar data or you had turbulent data. Sometimes it's where you stand in the room because of the air circulation in the room. Sometimes it's how nicely your coffee filters stay folded. If they start to expand, we tend to get more turbulent drag. If they stay nice and in like that cup shape, we tend to get more laminate drag. So I can't tell you which one of these you're going to experience. You just got to take both sets of data, or one set of data, and try linearizing it, assuming it's linear, or try linearizing it, assuming it's quadratic. And if you don't know about linearization of data because your teacher didn't do it last year, don't worry, we'll be talking about it. The data you will collect is straightforward. You will collect the velocity versus the mass. That's the only thing we can change here is the mass of the coffee filters. So you drop one coffee filter and measure its velocity. Then you stack another coffee filter inside the first and you drop it again. And you stack a third one and drop it again. And you kind of see where this is going, don't you? So you just continuously drop coffee filters until you've dropped them. You try to get as many as you can reasonably with the amount of coffee filters we have. Usually once you get to like the 6th or 7th coffee filter, they start dropping too fast to get any reliable data. Now you folks at home, you can actually do this with a stopwatch because we reach terminal velocity almost immediately. Your data will be almost as good as those people who are taking their data using a motion sensor. But also, if you want to take your data using video physics, that would be best. Video physics will calculate the velocity for you by videoing it as it drops. However, video physics is no longer the bargain basement price of free. It's now the, well, for an app, it's way high. It's $5. So if you didn't get it back when it was free last year and you want to do this lab using the video physics app, then it's going to cost you $5. However, I will throw this incentive. If I can get good video data from one of you, then I can reuse it year after year after year. That would be worth something to me. And that goes for anybody in the classroom too. If you want to use video physics instead, I would prefer to try and use that than use the app, the lab quests. So I will provide extra credit if I can get 5 good videos starting with 1 filter up to 5 filters. Does everybody understand what I'm saying? You will tomorrow when we do the lab a little bit more, but that's what I'd like. Now, ultimately, your data set for tomorrow is going to look like that. You're going to take velocity versus mass data. And then we are going to plot velocity on the horizontal axis and mass on the vertical axis. And then you will plot it again, but you'll plot velocity squared, and you'll see which one is more linear. I will show you a couple different ways to determine which one is more linear, but you guys who have had statistics know that you're looking at the correlation coefficient. That's how you can determine which one is more linear. So that's tomorrow's lab. It does not take long to take the data, but I wanted to kind of give you an explanation about it first. Do you guys have any questions?
Mr. Shelton,
Yeah.
what is C in that equation?
In both equations, C represents the coefficient of drag. However,
Okay.
as you can probably tell from that, just what I'm putting there, these are not the same value because the units wouldn't work out that way. The coefficient of drag is a combination of elements, but the coefficient is different between laminar drag and turbulent drag. So although we use the letter C, the truth is I should have C for laminar drag and C for turbulent drag to recognize that there are different values. Okay?
Okay, thank you.
Now, that's tomorrow's lab. I've given it to you at the front end of class. Are there any questions to this point about what we're going to do tomorrow? When you come in tomorrow, there'll be stacks of coffee filters. I'm going to spend some time helping the folks at home get set up for how they're going to take their data. I don't believe I have to do that with you guys. The lab quests are out there and the motion sensors are out there. You need to drop up to 8 or 9 coffee filters. You need to get reliable data for velocity and mass. The hardest part is you need to get the mass of a coffee filter. And that's pretty hard to do. So I'll explain how it's done, and we will have to pass that data to the people at home because they will probably not have an accurate enough balance to take the mass of coffee filters. But it shouldn't be challenging. Once we get the value, you guys can have it. All right. What happens in the middle? What I mean is, we talked about the steady state condition, and we talked about the instant it was dropped. If you want to understand what I really want you to be able to do in this class, you have to understand the middle part. Here's where we're not talking about the coffee filter lab anymore. We're talking about Newton's laws. You see, in the middle, the net force doesn't equal 0, but equals ma. But there are 2 forces acting in the system. There's mg downwards, and let's just look at laminar drag for a minute. There's CV upwards. Those are the only 2 forces acting in the system. So if I were to use my rules that we talked about for how to solve a Newton's law problem, I have my free body diagram. I have my forces all acting in one dimension, so I don't have to put in a coordinate system. I can choose a direction that I'm going to call positive, and then I can identify which law to use. I've done all those things now. So I'm going to put the forces in there, mg minus cv, and set that equal to ma. The problem is that in this example, which, by the way, I don't have numbers here. I don't need numbers. The acceleration is always changing. If you look at this, there is no way to get an easy answer for what the acceleration of the system is. The object is accelerating, which means that v is getting to be a bigger number. And as v becomes a bigger number, the acceleration becomes a smaller number. If I want to know what the acceleration of the system is, I'm no longer asking for a number. I'm asking for an expression, the acceleration as a function of time. I told you before that Newton's laws can only tell you a force or an acceleration. But what I didn't indicate is that acceleration could be a function as opposed to that acceleration being a number, which would suggest that there's an expectation that your math might get more complex. What I'm about to show you is something that those of you who have had calculus know about, and those of you who are in calculus right now have not learned yet. But I need you to pay attention to this. In this example, we use Newton's laws to create a custom relationship that we could then use to analyze this system. This custom relationship, though, is not a normal equation. Acceleration and velocity are related because acceleration is the derivative of velocity, which means this equation is actually a differential equation. A differential equation is just that. It is a function with a differential in it. This equation states that the rate of change of the velocity is related to the velocity. Now, you will have to know how to do 3 things related to differential equations. One of them is easy. The other 2, not so much. First, you will have to create a differential equation. There are 3 ways that we do that. You've just learned the first. The first way to create a differential equation is to use Newton's laws and replace acceleration with dv dt. This is specifically what I need you to learn how to do. So I'll say it again. We use Newton's laws very often to create a function for the acceleration. We do that by solving Newton's laws and then replacing the acceleration with its differential form, dv dt. So the first thing I will need you to learn how to do is to create a differential equation. This is one way to do so. It is highly likely in the exam you'll be asked to create a differential equation. It's asked every other year. This is only worth like 1 or 2 points creating a differential equation. But all you have to do is make this one replacement and you've created a differential equation. Second, I need you to learn something called separation of variables. It is a method for solving differential equations. And although I do not expect you to be able to do that yet, I do expect that you can follow along with the process, which is not hard. Separation of variables sounds exactly like what you would expect it to be. You're going to separate variables so that variables appear only on one side of an equation. In this case, that separation already exists. To separate variables, you have to split your derivative. I've split my derivative. I multiplied both sides by dt. We're moving towards a separated system. Once you've done that, you need to get anything with v in it to the same side of the equation as dv, and anything with t in it to the same side of the equation as dt. Now, if you've looked carefully, you should notice that there is no t here. So the only thing I have to do is make sure this gets moved over to the other side of the equation. The third thing you have to do is integrate both sides. That's outside of our purview today. We can't do that today. Too few of you have this skill. You will, but you don't right now. You need many things in order to do this derivative. Do this integral. This is not like the antiderivatives we did a couple weeks ago. This one's tough. This requires things you don't know, like U substitution, and the fact that this is going to be the natural log as part of our answer. There's a lot to go on after this step, but one of the things we do with Newton's laws is create differential equations, and every single one that we will create, we will solve by separation of variables. You should be able to do the first 2 steps of separation of variables: splitting your derivative and collecting your variables. I expect that you can get from a Newton's law function like that. There. I expect you to be able to get from Newton's law to this relationship, because it's just algebra. But this is how what we're going to do with Newton's laws is different than what we did last year. And it won't just be this. We see these kinds of expressions with acceleration all the time. Our acceleration can be a function because it can often be related to the velocity. And this is where we tend to see that. So I'm going to pause for just a minute. The difference between kinetic and static friction. Last year, you didn't talk too much about it. Static friction was starting friction. Kinetic friction was sliding friction, which means this one occurs only when the velocity is 0. This one occurs when the velocity is not 0. It's that straightforward. To understand friction, though, is to understand that there's an interaction between surfaces that creates friction. Friction's not bad. People tend to think friction is bad, but we need friction. Without it, nothing would ever happen in our world. We need the ability to gain traction, and that's what friction really is. The thing about friction that you will eventually learn is that friction takes energy away from all systems. It just wastes energy. It transforms energy into a version that has no good use, or at least no mechanical use. But friction is required. We need to have traction. We need to be able to stick to surfaces. Otherwise, we wouldn't be able to do anything. We wouldn't be able to do any physical work. So when we talk about the two kinds of friction, please understand that friction occurs because of an interaction at the boundary between two surfaces. Friction is a percentage of the normal force. It is a percentage of the normal force. In fact, we define how much friction there is by how sticky the surfaces are. And that stickiness is quite simply the ratio of the frictional force to the normal force. This produces a unitless percentage. We call this percentage the coefficient of friction. But for whatever reason, people become weirded out by the term coefficient of friction. Having taught this for years, I think part of it is because a Greek letter is used for it, the Greek letter mu. But I think the other part of it is because for some reason the word coefficient seems to freak people out, when all it is the number before a number. But what you must understand is that it's a percentage. It's how much friction do I get for my normal force. What's critical here is that if you need to increase friction, you can do so by increasing the normal force. You can press surfaces more closely together to ramp up the normal force. But generally, this coefficient is a number between 0 and 1. Anytime you get a coefficient greater than 1, the problem writer screwed up, or worse, you're dealing with glue or something like that. Generally, coefficients are relatively small. They're going to be somewhere between 0.3 and 0.7. Like your shoes, they're probably pretty high. They're probably close to 0.7, maybe 0.8. Your tires on the ground, 0.7, 0.8. But, we try to minimize friction by using lubricants and oils and such. So generally, you can have really small coefficients of friction. Anything under 0.1 and you wouldn't be able to have enough traction to walk around the floor. You'd be slipping all over the place and sliding. So it's just a ratio. The distinction is that the coefficient of kinetic friction is a straightforward value in that once you break static friction and you are sliding, we tend to treat friction as a constant, which is good. It means we don't have any weird relationships that deal with friction. However, static friction is an inequality. And what this means is that the amount of friction that we get from a surface can increase until you reach some maximum threshold. That's what this means. That the frictional amount can increase until you reach some maximum threshold. Once you meet that maximum threshold, you can defeat static friction, and then kinetic friction takes over. In general, static friction is almost always greater for the same surfaces as kinetic friction. This is why it takes more force to get something started moving than it usually takes to keep something moving. We have to overcome the static friction first. Once we do so, the kinetic friction takes over. Although you didn't notice this, it was purposeful that I didn't put bars over the top of friction and normal force. Because this is not a vector equation. Friction and normal force are explicitly in different directions. In fact, if I was to put anything in your notes, it would be to say, and put this in a box, that friction must be perpendicular to the normal force. Friction must be perpendicular to the normal force. Now, everything that was just said was all stuff from last year or any other person's first year physics class. Nothing really particularly interesting. Is there anything there I brought up that requires you guys to hear it again or need me to repeat? All right, so repeat from yesterday here. 5 kilogram box. Let's go with that 45 Newton force. Angle of, what did I do for an angle yesterday? 30? And coefficient of friction this time of 0.3. I'd like the acceleration of this system. Everybody understand what's being asked of them? All right. Take a moment, work it out. Again, I still feel like we are really just looking at review.